As an engineer, do you wonder about how Coulomb earth pressure theory actually works? You might wonder, where does the earth pressure coefficient come from? You might ask yourself, does it matter if the wall I'm designing looks like the one that's in my textbook? I know I've asked these questions. Let's take a minute, review Coulomb's earth pressure theory, and then use my favorite visualization tool, wall in a box, and see what it actually looks like. Coulomb earth pressure theory is certainly one of the most commonly used methods to calculate earth pressure on retaining walls. Funny enough, it isn't a new theory. In fact, it comes from an essay that Coulomb presented to the French Academy back in 1773. As it turns out, Coulomb's earth pressure theory is rather elegant. To understand it, let's consider a slightly simplified version of the theory and determine the force from retained earth on a wall. We start by making some assumptions. First, we assume that the soil is homogeneous and isotropic and has an effective angle of internal friction of phi. We assume that the slope on top of the wall is constant and at an angle beta measured from horizontal. We assume that the back of the wall is constant and at an angle theta from horizontal. We assume that there is friction between the retained soil and the back of the wall. We assume that the wall is long, resulting in a two-dimensional plane strain condition. We assume that the soil is right on the verge of failing. That failure angle is angle alpha measured from horizontal. We assume that the soil wedge that forms is a rigid body undergoing translation. With all these assumptions in place, we can draw a free-body diagram of the soil wedge and all the forces that are going to be applied. To start, we know how heavy the soil is, and so we can calculate the weight of the soil wedge based on the area of the triangle. We know that the wedge is supported by the soil underneath. We can model this support with a normal force applied perpendicular to the assumed failure plane. And then one of our basic assumptions was that the soil wedge was just about to fail, so we have a shear force acting along the assumed failure plane. We know that the wedge is also supported by the retaining wall, so we'll add a force on the soil wedge that is perpendicular to the back of the wall. Finally, there's friction between the wall and the retained soil, so we'll add the friction force along the back of the wall. Here's where we can start simplifying things. You might remember Moore's circle from your soil mechanics class. Basically, there's a direct relationship between normal stress and shear stress in a soil. As a result, we can replace the shear force and the normal force on the assumed failure plane with a resultant force acting at the angle phi. Now, it might take you a minute to see what's going on, but trust me, this works. I spent a lot of time looking at this, and when you realize that basically shear force is the normal force multiplied by the tangent of the internal friction angle of the soil, you can just take both those forces out, replace them with the resultant that acts at the angle phi. We can do something similar at the back of the wall. If we remember from physics, friction force is basically a normal load multiplied by a coefficient of friction. While in the retaining wall world, we use delta for the friction angle between the retained soil and the back of the wall. Tangent of delta is essentially our coefficient of friction. So we replace the force on the wall and the friction on the back of the wall with an active earth pressure force that acts at an angle delta from perpendicular to the back of the wall. From here, we can do some simple statics. We're going to sum all the forces in the horizontal and vertical directions and set them equal to 0. We can take these equations, we can combine them, and we can reduce until we get an equation for the active earth pressure force, P sub A. If we wanted to, we could assume different values for the angle alpha, and we could calculate the active earth pressure force for each of those angles. Of course, that's a lot of work. Fortunately, all we're trying to do is determine a local maximum for a quadratic function. If we pretend we're back in calculus class, we can take the derivative of P sub A with respect to alpha, we can set it equal to 0, and we can solve for the value of alpha that gives us our largest force. We can then put that critical value back into our equation for P sub A and reduce. The math gets pretty scary, and if you're like me at all, you're probably going to end up lost in the middle of a sea of trigonometric identities. However, if you can make it through, you're going to get a formula for active earth pressure that acts on the wall. Now, I'm sure all the geotechnical engineers watching have already noticed that the big fraction in this equation, it's actually the formula we use to calculate the Coulomb active earth pressure coefficient. Pretty cool. So all this math is fun, but does it actually happen in real life? Well, we can put it to the test with wall in a box. Here, you can see a simple gravity wall we built to fail on purpose. When we move the supports out of the way, you'll see what happens. As things start to move, you could notice the failure wedge that forms in the retained soil, just like our theory predicts. You might also notice the soil moving down the back of the wall, causing the friction, which we had also assumed. Here, you can see a simple cantilever wall. When we move the support out of the way and things start to move, just as expected, you're actually going to see this failure plane that forms from the back of the heel on the wall. It's also interesting to note the failure wedge that develops above the heel. Part of the supported soil actually acts like part of the wall to resist sliding and overturning. The last wall we'll look at is a PMB wall with 3 different width units. Again, the failure plane forms at the back bottom corner of the bottom unit. If you're interested in learning more about Coulomb earth pressure theory or PME walls, I invite you to download a copy of the Precast Modular Block Design Manual. And if you have questions about retaining walls for your next project, you can contact our civil engineering team. We are always happy to help folks understand how our PMB wall systems can help meet your specific needs. After all, we want you to design with confidence.